In this video we're going to look at how to calculate the transmission function of an instrument using a set of gold spectra that are measured at different pass energies of the instrument. The pass energy is important because it determines the number of electrons that will arrive at the detector simply on the basis of the hemispherical analyzer. When you adjust the pass energy, you also have to adjust the lens column, because the lens column must retard electrons of a given energy to the pass energy of the hemispherical analyzer, because only electrons close to the pass energy will be detected. So we have a way of altering the amount of signal that we record as a function of both the kinetic energy and also the pass energy. These two things together will allow us to calculate the transmission function. The data set I'm going to use to calculate the transmission function contains a set of survey spectra, all measured at different pass energies. We're going to collect data based on these regions. Each region provides an intensity. It also provides a kinetic energy. And since they're all measured at different pass energies, we also have a range of retard ratios, and that's what governs the transfer lens system. So we've got the intensity that ought to be identical if we divide each one by the pass energy that it's recorded. So that's what should happen if we had a perfect transmission of our lens column. But we don't. So when we take the ratio of the area to the pass energy, we get a number that is close to but not identical for the whole set. And that represents the variation in the transmission function. So from these regions, we'll calculate a data set that will then allow us to estimate the transmission function. So what I will do is I will select a set of these spectra. So I'm not going to use all. I'd like to have some that I'm going to extrapolate from the information I've got here to other pass energies, and that way the transmission function can at least be checked to see that it is doing sort of the right thing for different pass energies that are not part of the calculation. So I'm making a selection, and then I go to the spectrum processing dialog window, the intensity calibration, and there's a button here that says compute coefficients from regions in selected VAMAS blocks. There are my selected VAMAS blocks, and here are the regions, and these are the coefficients that are going to be calculated. So when I press the button, a new file is created, and in this file we have, for each region, we have a trace, and the trace is a plot of, let me just adjust the display so it tells me it's the normalized area divided by pass energy. So they're each one normalized at a point. You can see the point is here, and it is producing a set of curves that are almost identical for all of these different regions. So if I fit to these normalized areas plotted against the retard ratio, which is the characteristic variable of the transfer lens system, so that's going to be what I believe to be the transmission function for this instrument. And if I plot, let me see, if I go here and I change the display, we can see the points that we're going to fit. Here they are, and the fit using the polynomial is given by the green curve. So let's see now, let's just expand a bit. So here we see a pretty good fit to the set of data points that are normalized from the set of regions. So this represents the transmission function that ought to correct for the differences in the pass energies of the gold spectra. Let's go back to the data. Let me take this to a new VAMAS file so that I can work on these without worrying about upsetting my original calculation. So here we have a set of gold spectra, all at different pass energies, all different intensities. If I now bring up the spectrum processing again and go to the intensity calibration, I can apply this transmission curve to the selected VAMAS blocks. I'm going to do it to all of them. I'm just displaying the gold one for the moment. So when I press change the VG transmission function, this is based on a cubic polynomial that is used by Thermo for their calculation of the transmission function. So this is how you would correct given the coefficients from a Thermo file, but this is a set of coefficients that have been calculated from the gold spectra, and I apply to these selected VAMAS blocks this transmission function. So let me look at the gold only now. And so I've made a selection of the gold. I've added the transmission function to all of these data. If I want to see what they look like when I normalize these spectra with respect to the transmission function, which should take account of the pass energy and the transmission of the transfer lens. So when I say apply and then propagate that, I end up with all of the spectra now corrected for the transmission of the instrument, and they all overlay. Let's just see that one of them doesn't, and that's pass energy 10. So pass energy 10 is not working exactly the same as 20 to 200, but right now it looks like we've got a pretty good approximation to a transmission function, because when I apply it to the data, all the spectra overlay. You can actually see, if you look at the gold spectrum for F photoemission peak, that the resolution is changing, and yet the backgrounds all match. So this is the first test to say that we do have something that is plausible for a transmission function. The next test I will perform is to calculate areas of photoemission peaks. Now I calculated the transmission function based on the gold spectra, so it's a self-consistent argument to look at gold peaks. Let's have a look at the copper peaks. Let's see what we've got here, and we have some regions already defined. We'll delete these and place on photoemission peaks regions that I can then calculate the area. So that's the 2p 3/2 peak. I'm going to zoom and create. So let's see what we've got. A Shirley background, that's probably plausible for a copper. So that would do for defining the area of the copper 2p 3/2 peak. Let's now do a comparison to, let's see now, the copper 3p. And again, a Shirley background, that's plausible. So we need to now propagate these two regions. Let's first of all check that everything will work. I've got Schofield cross sections here. I've got the transmission is active, that's the one that I've just assigned to these data as part of this calculation. The escape depth correction, which is necessary for the Schofield cross sections, that's active, and we've got a bulk material in the form of a copper foil, so that's good. Let's just propagate. And so now I have regions on all of these copper spectra, regardless of pass energy. Okay, let's just check. And we've got low resolution, that our region is really working. No, I want to adjust that a little bit more. And hopefully when I apply that across the entire range, it will work for my high resolution data too. And yes, that's good enough. Okay, so let's look at the area that we calculate from these two photoemission lines based on a Shirley background and integrating the signal, correcting for relative sensitivity factor and correcting for the transmission function. So when we apply that, what do we get? Well, if we look simply at the percentage, they look pretty good across the entire range. The real test is in the area, and the area is very much consistent here. You can see that it's not quite so consistent over here at the pass energy 200. That's plausible because I did not scale the transmission function or calculate the transmission function based on the pass energy 200. I went from 30 to 140, and all of these seem reasonably good in terms of the area for both. So that is working quite well. The next test I will do is to compare the gold spectra that are corrected against a spectrum that was measured and corrected for the National Physical Laboratory transmission correction. So this spectrum here is a gold spectrum that was measured on an instrument that was then calibrated using the NPL system, and I want to compare the results that I've got against this spectrum here. So let's copy that into a file. So that's my corrected gold spectrum, and I also want to take from my file that has the corrected spectra. There they are. So I will take all of those and copy that into the same file as my NPL spectrum. Now what I would like to do is look at how these all compare. Now to do this I'm going to have to do a few little tricks, and that is, first of all, I want to align these spectra so they are all in the same column. So I've given them the same element transition field. I would like to also reduce the number of data bins. This has got a lot of zeros up here, so I'm going to use another trick and create myself a region that will exclude signal that is 0, and I'm going to propagate that to these data. So now each and every one of these has something that looks plausible. You can see that the range of this exceeds the spectrum that I have as my reference spectrum. So that's another reason why I want to do this. So I'm going to overlay these and then use a toolbar button to pick out spectra that are based on the regions. Now unfortunately the regions all have the same name, so it's going to produce a set of VAMAS blocks all with the same information for the label, but that's okay. We know that they come from these different pass energies, and we'll have to remember that. So here we have the new file that has got all of these data that are now sort of aligned, but you can see just here this is the reference spectrum. It's too small. So what I want to do now is normalize these in a systematic way, and one of the things I can do is rebin the spectra so that all these spectra have the same number of data bins, and that's important for the normalization that I'm about to perform, and that normalization is here. This is a Euclidean norm that I will apply to these data. So let me do that normalization and we'll copy them. Okay, so this is my reference spectrum, and this is what it looks like calculated with a transmission corrected calculation that I've just performed. So there we can see there are some differences here, a little bit of differences, not too surprising. If I start using arrow keys and start stepping up, you can see that as I get into the range of data that was used to do the calculation, I'm getting pretty close to what the NPL data looks like. So that looks like a good match. So we are recovering from this calculation the transmission function that will correct data almost as well. Oops, I shouldn't do that. So there is, because I normalized, the information about the time disappeared, and so I had to change from counts per second to the process counts, and now you can see that pass energy 40 is really quite close to the NPL corrected data, and that's reassuring. So we're as right in our calculation here as the NPL calculation.